Hi everyone, I'm Zeyu. Today I will be presenting our paper, Optimal Algorithms for Multiwinner Elections and Chamberlin-Courant Rule. This is the joint work with Professor Kamesh, Munagala, and Kangning Wang. To begin with, I will first introduce the concept of a multiwinner election. Essentially, there is a set of n voters, a set of m candidates, and each voter submits a permutation of the m candidates, indicating her preference. Now our goal is to find a set of k candidates out of them, and we call this set of k candidates as a committee. So let's consider the following example. Say there are 4 voters and 4 candidates. The voters are from B1 to B4, and the candidates are from A to D. Now the question is, how can we find a good committee out of them? Or even, how can we measure how good or how bad a committee is? Intuitively, choosing Alice is better than choosing David here, but we would like to quantify this. And actually, Chamberlin-Courant rule is just a very natural and prevalent way of quantifying the quality of a committee. And this will also be the protagonist of our presentation today. Before introducing the Chamberlin-Courant rule, I will first introduce the s-Borda score. The idea behind the s-Borda score is very intuitive. The s-Borda score of a candidate for a voter is just equal to its rank for that voter. And the s-Borda score of a committee is just the average of the s-Borda score of the top candidate for each voter. So intuitively, the lower the s-Borda score, the better a committee is, because more voters are able to get their more preferred candidates. And actually, the Chamberlin-Courant rule just aims to minimize the s-Borda score. Let's again consider the following election as an example. Say we want to select a committee of size 2. Now the optimal choice would be to choose Bob and Catherine, because in this way, all the voters are able to get their top choice. The s-Borda score here is just 1. As the main thread of our presentation, I will introduce multiple algorithms for Chamberlin-Courant rule, including a very natural greedy algorithm and an effective heuristic known as the Benjaf rule. I will first introduce the greedy algorithm. As you might imagine, the greedy algorithm just iteratively adds the candidate that decreases the s-Borda score the most. In other words, in each iteration, the greedy algorithm looks for the best candidate that hasn't been added and adds it to the committee. For our further analysis, we define the following notation. Let's define RTK to be the s-Borda score of committee TK. So let's look at the following example for greedy for a better understanding. Recall that RTK is the s-Borda score of the committee TK, and we again look at the following election. In the first iteration, greedy will choose Alice because the committee consisting only of Alice has a s-Borda score of 2, while the committee consisting either of Bob or Catherine has a s-Borda score of 2.5, and the s-Borda score of the committee consisting only of David is 3. In the second iteration, greedy will choose either Bob or Catherine because choose either of them will decrease the s-Borda score from 2 to 1.5. More interestingly, we can see that the choice of greedy is not optimal here. And since as we have discussed, the optimal choice here is Bob and Catherine, but greedy will always choose Alice. This reminds us that we should not expect greedy to produce the optimal result to begin with. There has been many previous works on providing an upper bound for the s-Borda score of a committee produced by some sort of algorithms, including a submodularity-based analysis of this greedy algorithm, and algorithm P which achieves the best currently known bound. And in our work, we will improve upon all the previous analysis and show that greedy algorithm actually achieves an upper bound of 2 times n plus 1 over k plus 1, together with an almost matching lower bound. In other words, we will show that the committee produced by greedy algorithm in k iterations has a s-Borda score of at most 2 times n plus 1 over k plus 1. The sketch of the proof goes as follows. Essentially, we will apply induction on K. The induction hypothesis and what we want to show are given as follows. In order to proceed from the induction hypothesis to what we want to show, we need to make a couple of useful observations. The first observation is that the Borda score of Tk is upper bounded by the Borda score of Tk-1. This is almost immediate because Tk is simply obtained from adding one more candidate to Tk-1, and adding that candidate will not increase the Borda score. This is a trivial observation, but this observation proves to be very useful, because if we already have the Borda score of Tk-1 to be upper bounded by 2 times n plus 1 over k plus 1, which is the objective, then we are already done. Thus, we only need to consider the case where the Borda score of Tk-1 is at least 2 times n plus 1 over k plus 1. This provides a lower bound on the Borda score of Tk-1, and as we will see, this guarantees a large potential improvement in the next step of greedy. The second observation is that the next candidate chosen by greedy is at least as good as average. This is also almost immediate because in each step, the greedy wants to find the best candidate, and the best candidate is of course at least as good as average. This observation is useful in the sense that it guarantees that the next candidate chosen by greedy can at least fill up a fair amount of gap between the current solution and the optimum. The ultimate observation is that by Cauchy inequality, we have the overall improvement per step has a quadratic dependence on the gap between the current solution and the optimum, so that when the gap is large, the improvement will also be large. Recall that we only need to consider the case where the Borda score of Tk-1 has a good lower bound, so this guarantees a large gap, thus guaranteeing a large potential improvement, which enables us to push through the inductive step. Here is a visualization of how we could push through the inductive step. Then we show an almost matching lower bound of 1.962. Essentially, we will show that there exists an instance where the Borda score of Tk is lower bounded by 1.962 times n plus 1 over k plus 1. Unlike before, where we used to see the preference profile of an election as a rectangular table, in this construction, we see the preference profile as a cylinder instead. We can understand this as follows. Let's imagine we scroll this rectangular table around so that the first voter meets the last voter, and the set of voters form a circle on the top of the cylinder. The candidate still goes from the top of the cylinder to the bottom in decreasing preference order. So actually, the preference profile represented by this cylinder is exactly the same as before. There is still a set of voters, and each voter has a preference for the candidates. The only thing that is different is our way of presentation. The basic setup of our construction goes as follows. We divide the candidates into two types. One is dummy candidate and the other is critical candidate, where the number of dummy candidates is far greater than the number of critical candidates. We will let the critical candidates to lie on the spiral. And essentially, what we want is that the greedy algorithm only chooses the critical candidates while choosing none of the dummy candidates. And we note here that the reason why we are portraying the preference profile as a cylinder instead of as a rectangular table is because of this spiral. Moreover, we let the number of voters and the number of candidates to both go to infinity so that we can see everything as continuous here, which will make our analysis more convenient. Here is a visualization of our construction. We can see that the critical candidates lie on the spiral, which is colored in red. The spiral gradually grows up. The voters lies on the top circle of the cylinder. The candidates goes from the top to the bottom in decreasing preference order. The dummy candidates lie in the rest of the white space. The spiral is organized in such a special way, such that the following observations are available. First, greedy will only choose the critical candidates. And second, the greedy chooses the critical candidates in order. In particular, the greedy will first choose the lower layer candidates before choosing the higher layer ones. In this instance, the Cauchy inequality in the proof for the upper bound of greedy is almost tight, so this enables us to achieve the desired lower bound of 1.962. As you might have noticed, n plus 1 over k plus 1 occurs quite frequently in our analysis, and this motivates us to define this as a benchmark. More interestingly, this is exactly the expected s-Borda score achieved by randomly selecting k candidates. Thus, we call this benchmark as rand. For example, our previous result can be reformulated as follows. Greedy is upper bounded by 2 times rand. So now a natural question is, can we do better than this benchmark? And if so, by how much? Our further analysis will show that we actually cannot do much better. We will show this with a hardness result. We use OBT to denote the s-Borda score of the optimal committee, and the hardness result goes as follows. Even if OBT is small, the best achievable upper bound of any polynomial time algorithm is still rand. Therefore, we call any efficient algorithm achieving rand as an optimal algorithm. Now a natural question is, does an optimal algorithm actually exist? And if so, what is this? Clearly, an optimal randomized algorithm exists because we can only achieve this by randomly selecting k candidates. Now, what if we want a deterministic optimal algorithm? We could just de-randomize that randomized algorithm. And actually, this de-randomized algorithm has appeared in previous papers as an effective heuristic known as the Benjov algorithm. The Benjov algorithm goes as follows. It iteratively picks the candidate that gives the best expected performance if the rest of the committee is randomly constructed. Since Benjov works in polynomial time and its performance is upper bounded by rand, thus Benjov qualifies as an optimal algorithm. Next, we look at our results in the maximization version. The maximization version of the s-Borda score goes as follows. Essentially, it simply reverses the score in the minimization version. The score of a candidate C for voter V is just n plus 1 minus the s-Borda score of C for B. And the score of a committee is just n plus 1 minus the s-Borda score of that committee. For example, in the previous election, the top-ranking candidate will now have a score of 4, while the lowest-ranking candidate now has a score of 1. Since most of the results in the previous papers are formulated in the maximization version, we'll also present our results in the maximization version as follows. Now, greedy is a 1 minus 2 over k plus 1 approximation. Benjov is a 1 minus 1 over k plus 1 approximation. And for the hardness result, there is no polynomial time, 1 minus 0.99 k plus 1 approximation. All these results follow almost immediately from their corresponding results in the minimization version. We also have 2 extensions to our results. The first extension is a lower bound for committee monotone rules. Essentially, we say a rule is committee monotone if the committee produced by it in k iterations is a subset of the committee produced by it in the k plus first iteration. For example, say a rule produces a committee AB in the second iteration and produces A, B, and C in the third iteration. Then, this rule can be committee monotone. On the contrary, if a rule produces a committee AB in the second iteration while producing B, C, and D in the third iteration, then this rule cannot be committee monotone. It's not hard to show that greedy is committee monotone while Benjov is not, because the committee produced by Benjov does not depend on K. The lower bound goes as follows. For any committee monotone rule R, there is an instance where R is lower bounded by 1.015 times rand. So this actually says that any committee monotone rule cannot be optimal, and this also provides an excuse for why greedy is not optimal. This actually shows a trade-off between committee monotonicity and optimality. The next extension is about core stability. We showed in our paper that core achieves a stronger notion of proportionality than s-Borda score. Anyone who is interested can refer to our paper for more details about how this actually works. Next, we extend our results to s-Borda score. The definition for the s-Borda score goes as follows. The s-Borda score of a committee is just the average sum of s-Borda score of the top S candidates for each voter, instead of the top candidate alone in the previous case. And we note here that the s-Borda score we just talked about is also known as the s-Borda score, which is a special case of s-Borda score. Let's again consider the following election as an example. Suppose S equals 2 and we want to choose 2 candidates. By enumeration, we can see that the optimal committee here is Alice and Bob or Alice and Catherine with a s-Borda score of 4.5. The results for the s-Borda score are given as follows. Since most of the results are just generalizations of those in the s-Borda case, so we'll discuss it only very briefly. We still use OPT to denote the s-Borda score of the optimal committee, and to let rand to be n plus 1 over k plus 1. The upper bound for Benjov and greedy are shown here. Moreover, there exists an instance where the performance of greedy is far worse than OPT. However, different from before, there is no fundamental barrier for us to improve this performance. So we designed an improved algorithm with dependent rounding such that the performance is far better than greedy when OPT is small. Ultimately, we present a couple of open questions. The first question is, what is the lower bound on the s-Borda score achievable by polynomial time algorithm? And in particular, does it match our upper bound for our improved algorithm? We suspect that the answer is yes, but we had some technical difficulties in proving this. The second question is, can we map the landscape of approximation ratios for generalizations such as committee scoring rules? And the third question is, can we apply our results to find approximate core solutions? All of these questions are interesting to explore more about. That's the end of our presentation. Thanks for everyone's attention.